So first, what exactly is a foundation agent? So we call it foundation because we think it can be a generalizable fundamental intelligent unit, which can be composed together to form powerful multi-agent system. Reasoning is more about your current decision making to decide what actions to take based on the current context. We want to combine the advantage of both system 1 style fast, intuitive reasoning with system 2 style more deliberated, like slow, deep reasoning. Basically, today's talk is about building the cognitive engine for foundation agents. So as I said, that is based on the comprehensive survey we have conducted. Let's ask a very simple question. So what is exactly an agent, right? So if we check the classical textbook actually from Berkeley, the Stuart Russell and Peter Novi, in that AI textbook, it says that an agent is anything that can be viewed as perceiving the environment through sensors and acting upon that environment through actuators. So basically, you have sensor to get perception signals from the environment, and through a cognitive process, you make decision about what actions to take, and the actuators will execute those actions, which will impact the environment and change its state. The mysterious part is this question mark, right? We call it the cognitive engine. So how exactly we can construct it? What kind of architecture it should have? So this is what we are quite interested in. So this figure is basically the quite classical from LM to LM agent figure, which is from Dr. Wen Lilian's blog. So you can see that with a pure LM, and we augment it with auxiliary modules like external memory, tool libraries, actions, and also augmenting its planning ability and so on. We comes up with quite simple and elegant LM agent framework. So with advancement in LM research, we have strong natural language understanding capability, reasoning capability, adaptivity, and so on. So the question we're interested in is where are we in the current AI research and what can be improved? So we know that LMs has strong capability and efficiency in different tasks and environments, but still not good enough in terms of, let's say, safety, trustworthy, and there are also still limitations in generalization, adaptability to different tasks and environments, and integration of different type of modules. And based on an overview of the current research landscape, we also want to think about what can be improved. We want to come up with a unified framework for AI agents, and based on it, we want to improve, let's say, lifelong learning, complex reasoning in specific domains, emotional grounding, multimodality, and so on. So basically, our idea is that we can make a comparison with human brain, right? Which is basically the most intelligent things we know in nature. By making a comparison with human brain, we're not trying to say that, okay, everything brain has is good and machine is not good. So that's not what we want to say. Also, we don't think that replicating every characteristic of human brain is really a good idea. But we want to know what is the gap, right? Well, and what we can do to bridging the gap, what we can learn from each other. If we consider from a high level manner, in the hardware level, they're different, right? One is from biological neurons, another is artificial neuron with tens of GPUs learn from large corpus of data. The energy efficiency is dramatically different. And human brain is conscious, and for AI agents or LM itself, from my perspective, I think it's still safe to say they're not conscious. And for learning style, our brain is naturally strong in perform lifelong learning, short learning, few-shot learning, continuous learning, and so on. And relatively, LMs are not so strong in terms of this. And creativity, I think we're still even more creative, and also we are socially, emotionally grounded, which is different for LMs and neural networks. And of course, this cannot cover all the difference there. So we further conducted some more specific capabilities. So we categorize different capability or different research topics into 3 levels. So let's say the green color indicates, okay, this kind of research is well developed. It doesn't mean that we should stop researching about it. It means that the performance is good enough for many real-world applications. So for example, language understanding, right? LMs are strong in this. Object face recognition or visual perception. This is due to the computer vision research, right? And ordinary processing, reflective response, those kind of are relatively well developed. And for the second level, we consider it is partially developed very important topics, but still we have a significant room to improve. So for example, the modeling of complex reasoning, planning, decision making, different type of memories, attention control, so multisensory integration and so on. So those are core topics in the current AI research, right? So and a lot of the research progress is based on LLMs, neural networks, and so on. But still, we have a long way to go, I think. And we like the current AI research, we are working on different topics, but how they can be better grouped together to form a unified framework. So this is what we're interested in. So first, what exactly is a foundation agent? So we call it foundation because we think it can be a generalizable fundamental intelligent unit, which can be composed together to form powerful multi-agent systems and solve different types of tasks in different types of environments. We think they have general cognitive capability and to enable them work for different tasks and environments. And we formally defined the what we call the agent loop. So if you check the definition, recap the definition from Berkeley textbook, right? So we're not sure what exactly is inside this cognitive part. So here we make it more clear by defining the core concepts about the mental state and the cognition function. So let's say start from the environment. We denote environment as a state, S of t, which is quite normal, just like most reinforced learning will do. And we have sensors, which defines a perception function, P, which turns the environmental state, ST, to observation, O of t. And we should note that the observation doesn't only depend on the external environmental state. It also depends on your internal state. So for example, if you have different mood or you have different context, you will pay attention to different types of informations outside, right? So that's why we define the O of t is equals to the perception function given the external environment and the mental state. And then with this observation, what we can do, we consider the cognitive process as like two-stage process. We have learning and we have reasoning. So for learning, it's more about the maintain and update of long-term internal structure. Here we define the internal structure, we call it mental states. It includes like world model, reward memory, goal, emotion, and so on. And this, I think, makes it both a rational and emotional intelligent machine. We define learning as update the mental state from MT minus 1 to MT based on action AT minus 1 and OT. So actually, if you consider it, it means based on your last mental state and your new observed experience, because experience includes your past action and your new observation, right? And this helps you to update the mental state. And then, based on the updated mental state, we reason about what actions to take. So reasoning is more about your current decision making to decide what actions to take based on the current context. So it's based on the M of t, and you produce A of t. And you can consider this action is a sort of an action. For example, maybe you want to execute some action in the physical world. So you need to turn it into executable real-world actions. So you have actor which can execute this action and impact the real world. So that's why we have execution. Based on this whole loop from step 1 to step 6, we define the whole perception, cognition, and action loop. And we make it more clear what kind of component is important and how they work together. So this is the illustration of what we call the foundation agents. So you can see it's a quite a high-level framework, but we want to emphasize what are the key points to make agent works well and can be composable to form multi-agent systems. Next, I will very briefly talk about the memory and the reasoning model. I'm not going to talk about many details, but so the first work is called R3-MERM, bridging the memory retention and retrieval via reversible compression. If you consider what we call memory, memory is the storage of your past information, right? You have two forms. One is you store it in explicit database, for example, vector database or relational database, graph database, whatever. In this case, like with more and more memory, the scale will increase, right? And it will make retrieval more challenging, but it can retain accurate information. Another way is implicit. You store memory in your network ways. So in this case, it's quite scalable because no matter how many information you have, as long as your memory doesn't change, you are basically learning through your memory. but maybe it's less reliable to maintain all the accurate information, right? So we want to bridging the gap between memory retention and retrieval. That's what we call the R3 So how it works? We have three core ideas. The first is we consider memory as a zip and unzip process. So check this figure. So it's like you have a long context. The memory is a compressed representation of your original context information, and the retrieval is given a concise short query. You want to unzip the original context. So we consider this a dual task. Then this makes us to construct a reversible memory network structure. And what we can do is we can turn the original pre-trained transformer-based language model into a reversible transformer language model and using parameter-efficient fine-tuning way to make it works. And this enables us to, let's say, we construct query context pair dataset by generating the summarization in different granularity from document level to paragraph to sentence to key entity level. And this forms the continual pre-training data. And then we use our transformer network with new designs, which makes it reversible as well as with memory tokens, so that we pre-train it, continue pre-train it on such a dataset. Then we turn an existing open source model, like Llama model, into a Llama memory network model. So this is what we're doing. And our experiments shows that it outperforms many different existing SOTA memory models. And we also try to incorporate our memory module into existing agent framework and compare it with other type of memory design, like memory bank, memory rack, and so on, and which shows that our R3 network outperforms all of them in terms of different dimensions like the response correctness, contextual coherence, ranking score, overall metric, and so on. So this work has been accepted by DCSACL, and the paper is also available on arXiv. The last recent research I want to share, which also I feel excited about it, is what we call System 1.5 reasoning. You can see from the name, right? System 1.5, which means we want to like combine the advantage of both System 1 style fast, intuitive reasoning with System 2 style more deliberated, like slow, deep reasoning. So how we can do it? If you ask existing LM models, which is fine-tuned with chain of thought style data, you will find that, okay, it can improve the accuracy of the answer, but it can be quite redundant. Even you ask a simple question, what is 2 plus 3? It can give you 5 solutions and finally confirm that, okay, the result is 5, which gives you 900 tokens, right? Which is ridiculous. And prior work, either trying to, let's say, either language level efficiency by producing faster and fewer cheaper tokens, or bypass the language constraint by reasoning the latent space. And we can check this figure. So let's say if you check the B chain of thought, which is you produce tokens step by step, right? Those yellow tokens are the reasoning process tokens. And finally, you got the orange token, which is the answer. Another way is early exit. Early exit means that, let's say if you have 20 layers transformer, you don't need to go through 20 layers every step, because for some steps, it's easier to reason about. So maybe you just need 1 layer or 3 layer, then you got the token. So this is the early exit to reduce the inference steps dynamically and compress the latent reasoning, which means I don't need to actually output the explicit token during the thinking process. I just continue updating the latent in the latent space. So this is what we call the latent reasoning. A typical work is the coconut, right? And finally, it's extra latent reasoning, which is like you have some special tokens like posts and so on to enlarge the reasoning process on critical steps. And all of this has some drawbacks. For example, they either keep consistent reasoning style. For example, no matter whether this step deserves deep reasoning or not, they keep using a consistent style, or they are keep using the tokens in the language. And what we call system 1.5 is like you can either go vertically, which is through the transformer latent layers, or you can go horizontally by providing a shortcut, which means, okay, this step is easy to reason about. Let's go quick to the next time step. So that's why we have designed this depth shortcut, which is vertical direction, and step shortcut, which is horizontal direction. By combining this, we want our model is like quite flexible, So it can be easily travels through the latent space. It's like you can go up, you can go right. So it's quite flexible. You can explore any path. And what does this mean? It means that every time when you reason about in the latent layer, you can either continue go through a deeper layer, which means I'm thinking more. I need to go from layer 10 to layer 11, or you can go horizontally. Okay, this step is quite clear. Let's continue reasoning. Or you can early exit, which means, okay, now I'm already know what is the answer. I can early exit. So this actually needs a gating mechanism, right? So we designed a gating mechanism to let the model to decide where to go at each depth, at each time step. And how we can learn such a gate mechanism. It requires to solve two challenges. You need to have that kind of data. You need to transform the LM from reasoning in the language space to in the latent space. And this is solved by two strategies. We utilize language to latent alignment and shortcut learning. Basically, language to latent alignment is that, okay, I have a teacher model which is already know how to perform chain of thought reasoning, right? Then we can extract their latent representation and align our latent representation with their latent representation. In this case, we don't need to produce tokens in the language space, but we can mimic the latent representation. And the second stage is shortcut learning. So shortcut learning means I need to know at each stage I should early exit, or I should continue my reasoning, or I should perform quick reasoning to go right? So this can be done by using the recent work Atom of Thoughts to decompose the question answering dataset and label out what are the key steps, what are fast steps. Then we have different labels, and we can, based on this label, we know at each token which gate state we should have. So basically what we found is that, okay, the performance is quite good. We can compare it with different baselines, and we maintain the accuracy, which is as good or even slightly better than self-thought reasoning. But we only need, let's say, 2 to 4 steps, which means just 2 to 4 time steps to perform the reasoning. And in comparison, those baselines needs more than 20 to 40 steps to reason about the answer. And also we speed up for more than 20 times. So which means we used much less reasoning steps, and we are much faster in reasoning, and the performance is as good as original chain of thought reasoning. Another key advantage is that we can easily control. So let's say if you have a memory reasoning model, as we described, then you have two buttons to control. One is called the lambda depth, which is basically a threshold value. If the value is higher, which means your model must have a higher confidence to decide, okay, I know the answer, I can early exit. Another is lambda step, which means how many reasoning steps I can use before I produce the answer. So you can see we don't need to fine tune or retrain the model. You just change this lambda step and lambda depth. You can control how many steps I can reason, how many depths I should reason. Then it balances the reasoning efficiency and reasoning effectiveness, the performance, right?
The training there when you were learning how to short circuit either vertically or horizontally, I was wondering, does your reinforcement learning, I guess you're doing that during a reinforcement learning state or something when it sounds like you're almost doing it during a supervised fine tuning from teacher latents, right? But
Yes.
Is there something in the objective that is incentivizing it to produce faster responses? Because if you're just getting the best response, there's nothing to say, find some way to skip layers. I was just trying to understand how it would be incentivized to say it's better off to get to the answer quicker and terminate.
This is about how we train this gate, right? We used an existing work which is called Atom of Thoughts. The idea is that, let's say if you have a question and you answer this question, actually in your answer, you can decompose it into different steps. And if you consider about the logical structure, you can characterize these different steps into a tree structure, right? You may have multiple subtrees and so on. So in this case, you can consider the roots of those subtrees are the key steps. It starts a thinking process. Trajectory is less critical because it naturally follows the previous thinking steps. And the reasoning challenge is less than those critical steps. So based on it, we can decompose reasoning dataset and label out this phrase is key steps, this phrase are not. Then we can decide, okay, here we can do more deep reasoning, here we can do faster reasoning and so on. So this is about how we decide the, like either go to the next time step or maintain here. And for whether go to deeper or not, it depends on the hyperparameter, the lambda depth. So if your output confidence is higher than this lambda depth, which means, okay, I already know the answer, I can early exit. So by combining the data labeling and this threshold, we can like fine tune the model to know when I can early exit, when I can like do more reasoning, or when I can do fast reasoning by horizontal shortcut.